Section 7.6, quadratic functions. There are two objectives here. The first is to analyze a quadratic function and draw its graph. And the second, to find the locations, or location, and the values, or value, of the extrema of the actual function. Let's first start by looking at the two different forms we're going to see a quadratic function in. And again, remember, a quadratic function is a parabola when it's graphed. So the first form we're going to take a look at is going to be standard form, or the general form. And it's just f of x equals, and just like our polynomials were, okay, ax squared plus bx plus c. If there were four terms, it'd be ax cubed plus bx squared plus cx plus d, etc., etc. Now, obviously, a is not 0 in this case. If a were 0, then this would just drop off, and this would be bx plus c, which is really a linear function, but we're looking at a quadratic function, so we have to have a square term. The other way to display this is in vertex form, and this is similar to what we looked at in the last section, but instead of having it as y minus k over here, we take the y and make it f of x, really, because that's what y is. It's a function of x. And we take the minus k and add it over. So see how there's a plus k over here? This plus k comes about from this side, instead not having been this. All right, this is our vertex form that we looked at. Well, vertex form, when we're looking at a function, so we can write it as a function f of x equals, we simply take the negative k and add it over here as a positive k, and this is now gone. Instead of writing y, we can write this as f of x. This is a function of x. Example 1 says, determine the vertex and axis of symmetry of the function f of x equals 3x squared minus 12x plus 7 by transforming it to vertex form using the method of completing the square. So we're going to take that function there and turn it into vertex form using completing the square. Then verify that the axis of symmetry in vertex form, which we know is x equals h, that is actually equal to x equals negative b over 2a. So that's a statement we're going with here. We're going to prove that that's true. So saying that this is the axis of symmetry when it's in its standard or general form, where this is a and this is b and this is c, and this turns out to be the same thing as putting it into vertex form and having x equals h as the axis of symmetry. So let's take a look at this one here. So let's start by writing this function with y equals instead, just to make it a little bit easier when we're moving things around. And then we'll put it back into f of x afterward. So we have plus 7 on the end there. Remember, with completing the square, the first idea is to move over the first term. So now we're going to have y minus 7 on this side equals 3x squared minus 12x. Now, the next step traditionally is to divide by whatever a is. Now, usually we do this completing the square method to find the roots of an equation, so we set y equal to 0 usually. So this is usually just a negative 7 here. It's usually a 0 here. This doesn't matter. So this is usually not there. Now, if we divide everything by 3, these clearly both simplify very easily, but this becomes negative 7/3, and this is then y minus 7 over 3. It's kind of odd. So what we're going to do, not odd, but it looks weird. What we're going to do is instead we're going to factor out the 3 in the front. And we'll see that in the end, it's the same thing as if we just divided by 3. The result is no different, really. Let's see. So we have this now. Right? That's what we get if we factor out a 3. Well, now what we'll do is we'll complete the square inside that parentheses, but remembering that there's a 3 on the outside. So we take, remember, we're looking at this portion right now here, and we say, here's the b value. What's half of this? Half of this is negative 2. And then we square it, and we add it right here to this spot. So it means half of this is negative 2. Negative 2 squared is 4, so we're going to put a plus 4 right there. So in reality, we're putting a plus 4 right there. Well, this 3, technically speaking, gets distributed back out if we did. So that's really putting a 12 there. So when we add it to this side, we have to just add 12 to this side. And that's the little trick there. Instead of dividing by a, we can factor out a, but remembering that really that 4 is really worth 12, because there's a 3 multiplier in the front that would be distributed to it. So this side becomes simply y plus 5. On this side we have a 3, and then this quantity, well, this is really just x minus 2, x minus 2. Remember, it's always going to work out that way. It's always going to be whatever half of this was ends up here and here. So this is just x minus 2 squared. So we're technically in vertex form now, but I'm going to move the... Well, I'll leave it like this, actually. I'm going to leave it like this. This is vertex form with y equals, but we could write it like this, right? We could write it as y equals 3 parentheses x minus 2 squared minus 5. And then replace y with f of x. And now it is in vertex form, but written as a function. Now, let's go back over here and just remember this first, though, because we studied this last section, and we remembered that the vertex was located at h comma k. So in this example, if we go ahead and take a look, and we analyze for a moment, well, x minus h, well, x minus 2. So h is just 2. Remember, h was taken the place of by 2 here. So the vertex already is going to be 2 comma something. Well, we have to then look and say, well, this is a plus 5, this is a minus k. Well, this has to be minus negative 5 in order for this to be a positive, right? Minus a negative. So k is negative 5. Now, we could have also just looked at the standard form over here, or the vertex form as a function, and seen that this gives us x minus h. Well, this is still 2 here. Well, this is, remember, in vertex form for a function, this is really a plus k, because we've taken this negative k and added it over here. So this negative 5 ends up being what we're looking for. So if we're looking at vertex form when written as a function, we could remember that here it's the opposite for h, right? This is, it looks like a negative 2, and that's a 2. And here it looks like a negative 5, and that is a negative 5. So whatever this is shows up. Again, that simply comes about because the vertex form written as a function is this. Right, see that plus k? And the plus k is kind of indicative of the fact that this is going to be the value that we're going to use. The minus h tells us to kind of use the opposite of what you see here. Well, it looks like a negative 2. It comes out to be a positive 2. So that's the vertex. Now, if that's the vertex, we know that the axis of symmetry, remember, axis of symmetry, which splits the parabola in half, is always x equals h. Well, h is 2, right? So there it is, x equals 2. So on this graph, already we know it looks like this. 2, negative 5. Well, we go over 2, and then down 5. So here's the vertex down here somewhere. We know that it's a positive a value, so it's going to open up clearly. So it's going to open up like that somehow. We don't know what the roots are, so I won't even guess to that. And then for now, we know that the axis symmetry goes through x equals 2. Okay, so we want to go back and look at the original function when it was in standard form and see if we get x equals 2 as our axis of symmetry if we go ahead and use that value that was stated earlier using, again, x equals negative b over 2a. So I'm going to do that over here. I'm going to say x equals, well, let's see what negative b is. I have negative b. Well, negative b is really negative 12, so it's going to be a positive 12. Okay, all right, I'm incorporating this negative up here with the b. And then over 2a, and that's over 2 times 3. Well, 12 over 6 is indeed 2. So the axis of symmetry of x equals 2 right here works if we use negative b over 2a. And if you want to derive this or see where this comes from, all you need to really do is go take a look at the transformation from standard form into completed square form. Okay, if you do that with general variables, so if you have this, and you transform that into completed square form, you'll see the negative b over 2a as the value for h there. So finally, the last thing, since we've done this now, we've now stated the fact that we have the following. When it's in vertex form, to find the axis of symmetry, you're simply going to use x equals h, and to find the vertex, it's h comma k. That's awesome. But now we have it in standard form. Okay, or general form. If it's in that form, now for the axis of symmetry, we're going to use x equals negative b over 2a. Well, that gives us the h value, right? Whatever this value here was earlier when it was in vertex form. Well, when you plug h in for x, whatever the axis of symmetry is, you get the k value, right? When you plug it into the function, you get the y value. So this is our x value, right, of the axis of symmetry. Well, the vertex, here say the axis of symmetry is here. The vertex has to occur somewhere on the axis of symmetry. So let's say that the vertex were here. Well, the x-coordinate is whatever negative b over 2a turns out to be. That's what the x-coordinate is. If this comes out to be 5, right, this is over 1, 2, 3, 4, 5 units. So it's 5, comma, say 7, or 5, comma, 8, or 5, comma, 9, whatever it goes up to. So this is the x value of the vertex right here. So the vertex, when it's in standard form, this is the x value, whatever that is. I'm just going to write it generally speaking, negative b over 2a. So if it were 7, it would just be a 7 there. How do you get the y value? Well, you plug that into the function. You take the x value, right? If you want to find what the y value is of a point, you plug in the x value into the function to get the y value. So this is really the function when you plug in the axis of symmetry's value. So that's my coordinate for my vertex when written in standard form. Whatever the axis symmetry is, put that in for x like we did here, the same thing. And then take that x value, plug it into the function, right? Plug it into the function to get the y value. And we'll do a few examples of those. Example 2, given g of x equals 3 plus 4x minus x squared, find the following. A, the vertex of the graph of g, B, the domain of g, C, the range of g, and D, the zeros of g. So let's start by putting it in the correct form. So we'll say g of x equals negative x squared plus 4x plus 3. Now, be careful here and don't try and take out a negative 1 right away, because we want to take a look at this and say, well, first we know that this is negative, so it's going to open down. So the graph is going to look like this. It's going to open downward. And then we can go ahead and calculate the values we need to find. So to find the vertex, though, we need to first find the axis of symmetry. So let's go ahead and find the axis of symmetry using x equals negative b over 2a. Again, this is for part A here. So we'll say x equals negative b over 2a, which is equal to negative 4 over 2 times negative 1, which is really equal to positive 2. So x equals 2 happens to be the axis of symmetry. Well, if that's the axis of symmetry, we just have to take that value. So the vertex we know already is going to be 2 comma something, right? So take the 2 and plug it in right here. So let's find out what g of 2 is. All right, see what the value of the vertex is, or the height of the vertex is, when 2 is its location. So we have negative, and remember this is 2 squared, so it's going to be a negative number there, plus 4 times 2 plus 3. And again, please be careful here. This is not negative 2 squared. It's the opposite of 2 squared. Well, 2 squared is really 4, so this is really the opposite of 4, which is negative 4. Plus 8 plus 3. That's 11, and a negative 4 is going to give us a 7. So 2 comma 7. That's our vertex for this graph of g. Part B says to find the domain of g, and remember the domain is really the values that the independent variable can take on. Well, if we think about what the graph of this looks like already, we know that it's at 2, 7. Well, 2 is over here and 7 up here, right? So let's go over 2 and then up 7. So we know that our vertex is going to be somewhere like this up here, and it's going to open down. Okay, we know that already because it's a negative leading coefficient. Well, the domain are the values that the independent variable can take on, and those are the x values. Well, here's the x-axis, here's the y-axis. It seems to me that x can go as far over, right? It keeps going over and over forever. And this way as well. X is going to go over and over forever. This graph is actually drawn a little bit out of proportion. I should really have this graph continuing over this way to show that it is going off at an angle. So yeah, the graph goes off forever like that. So the domain can be any value, really. So we say that the domain consists of all real values of x. So for part B, we could say this is our domain. For part C, we were trying to find out what the range is of this function. What is the range of the function? Well, we know that since a is negative, the parabola is going to open down, like we said, and the vertex is at 2, 7. So if we just take a quick look back up here, we could see that the range is all values below 7. Like the graph does not exist up here, right? There's no graph up here. Everything from 7, right, on the y-axis 7, on the x-axis was 2. Everything from 7 down is included in the graph, including 7. So all values less than or equal to 7 would be the range. So we say that y is less than or equal to 7. Finally, part D says to find the zeros of g. Well, to find the zeros of g, we have to set the quadratic equal to 0. So we get 0 equals negative x squared plus 4x plus 3. In this case, this is not factorable, so we'll use the quadratic formula. We'll say x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And as a result, I'll end up getting here 4 plus or minus root 28. Okay, all over, negative 4 all over negative 2. Now, if that's the case, what we end up having here is we can factor out a radical 4. Think of it this way as radical 4 times radical 7 again, and simplify. And what we'll notice is that this is really a 2, and therefore, since all of these have a common factor, we can simplify them all by a factor of 2. So everything reduces by a factor of 2, making the leading part simply negative 2 plus or minus radical 7 all over negative 1. Well, the negative negative has to happen, right? Let's divide everything by this negative 1 here that we see. So this becomes 2 minus or plus radical 7. And notice I did minus or plus there, which might seem a little bit weird at first, but it is technically the right way to write it, even though plus or minus is the same thing in this problem. Okay, but I'm just flipping the order of this sign because I divided by a negative, which means change the sign. So in essence, that's what it becomes. But again, it doesn't matter. Okay. One final thing to notice is that this value here, the first part, if you ever get a binomial conjugate or a complex conjugate as your results for the roots of a quadratic like this, using the quadratic formula, the first part you get will always be the same thing as the axis of symmetry. And you might ask yourself, well, why is that true? Well, let's see why that's true. The reason that's true is because, remember, the axis of symmetry is x equals negative b over 2a. That's the axis of symmetry. Well, the quadratic formula tells us this, negative b plus or minus the square root of b squared minus 4ac, and it's all over 2a, which means that these are both over 2a, really. So this first part is really negative b over 2a, and this is really b squared minus 4ac all under a square root over 2a. Well, this negative b over 2a, that's this right here. So this first portion of the quadratic formula, this negative 2 over negative 1, which turns out to be just 2, that's the same thing as you get for the axis of symmetry. And that is clearly apparent because our graph, the axis or the vertex was at 2, 7, and there was our axis of symmetry right there. Okay, so this is like your deviation really for your roots. Your roots are going to be located at 2 plus or minus radical 7. So one of your roots is going to be radical 7 units over, another root is going to be radical 7 units over. And radical 7 is something between 2 and 3 clearly, which is why I went past the y-axis there. So here's one of your roots, you know, for sure. And here's another root. And again, those gaps from the axis of symmetry, that's the plus or minus radical 7. That's how far away the roots are from the axis of symmetry. Let's quickly just reiterate something that we said earlier, but just to make sure that we're clear. To find the y-intercept of a function, we want to set x to 0 and just solve for y, which is really quite simple. But to find the x-intercepts, right, we're finding the roots of the equation, really. We're setting y to 0 and solving for x. So again, we're finding the roots of the quadratic. So we have 3 possibilities again. The last case that we just looked at, there were 2 roots, and it looked like this, except obviously the graph was inverted, right? It went over like this, but there were 2 intersections. We could also have where a quadratic just touches once, and that's when then a discriminant in the quadratic formula, right, the b squared minus 4ac, when that's equal to 0, you get just one root there, and it's a repeated root. And then finally, if the discriminant were negative, remember the roots are imaginary, and therefore we don't see them on the real graph here. We don't see any roots. There's no crossings on the x-axis because the roots here are imaginary, because the discriminant is indeed less than 0. Now let's take a look at the extrema of parabolas. So if we let f of x equal our general form, ax squared plus bx plus c of a quadratic, if we have 2 statements first, if a is greater than 0, well, when a is greater than 0, we know that the parabola opens up, right? That's this case. When a is positive, the parabola opens up. And therefore, there's going to be a little minimum value, like a valley. The bottom of a valley is the minimum. It's a low point. So you have a minimum value. If a is less than 0, it opens down. So it's opening down here. It's like a hill. On the hilltop, you have the top, or the highest value, which we call a maximum value. So these are the 2 correlations we want to remember. And now, finally, we should also take a look at our vocabulary here to remember that the value of an extremum, like the value of a max, like if I say the maximum value or the minimum value, that's the y-coordinate, really. That's what the value is, the y-coordinate. So let's say that this coordinate here we're looking at, right? Well, this coordinate here is clearly negative 1, 4. So the value of the max is 4. That's what the value is. The location of the extremum, or the maximum in this case, the location is the x-coordinate. The location is negative 1. So example 3 is quite simple. It says determine the maximum/minimum value of the following function, f of x equals 4x squared plus 8x minus 1, and find its location. So here we're trying to figure out, first of all, is it a max or a min? Let's start with that. We can see that since a is positive, the graph is going to open upwards, so it is going to be a minimum value. So we know already we're looking at a minimum. Well, the minimum, if we remember, say this is the xy axis, not that it is. The minimum occurs through the axis of symmetry, right? That's where it occurs. And the axis of symmetry gives us the location. So this location here, this length here, whatever this is, we can figure that out first by finding the axis of symmetry. We can go ahead and plug in. We'll get negative 8 over 2 times 4, which is negative 8 over 8, or negative 1. So we already know that the location is going to be at negative 1. It's going to go back a distance of negative 1 units here. The displacement, really. Now, that's the location of the minimum. What is the value of the minimum next means we have to find the y value. So we'll take negative 1 and plug it into the equation here and here. So we'll do f of negative 1 to figure out what the value is. Well, it's going to be 4 times the quantity negative 1 squared plus 8 times negative 1 minus 1. Well, if I simply just plug in my numbers here, it's going to be 4 minus 8 minus 1. Well, 4 minus 8 is going to be negative 4, minus 1 is going to be negative 5. So it turns out that the value is at negative 5. So the value of the minimum is negative 5, which means our graph was, close, but on the wrong side of the axis, clearly. But this was, again, just a random graph we drew. So it would be looking something like this, right? Okay, here's our vertex. It's a minimum value. Its location is negative 1, and its value is negative 5. Example 4 could be difficult, but we just have to think back to systems of equations. So let's keep that in mind the whole time. So we start by looking, and it says, find a function f of x equals ax squared plus bx plus c that has a y-intercept of 7 and contains the following 2 points. Well, if I have a y-intercept of 7 right away, that's the point, right? It's got to be 0, 7. So really, I'm given 3 points in this problem. If I'm given 3 points and I'm trying to find out what a, b, and c are, think about 3 equations, 3 variables. So plugging in those 3 points, I could start with 0, 7, right? F of x is 7, the value of the function, and then I have a times 0 squared plus b times 0 plus c. Plug in the second point, I have 10 equals a times 3 squared plus b times 3 plus c. And the third point I plug in, I have 25 equals a times negative 2 squared plus b times negative 2 plus c. Well, looking at the first equation, these drop off because they're zeros. Anything times 0 is 0. This tells us right away that c is equal to 7 in the first equation. So I don't need the first equation anymore, and I really can replace these with 7s now. And now what I've done is I've created only 2 equations and 2 variables. I need to solve for a and b, and I have 2 equations. So let's set them up as a system of linear equations. Again, we know c is 7 already, so let's find a and b. So this becomes 10 equals, this is going to be 9a plus 3b plus 7. So I'll change the 10, make that a 3, and get rid of the 7. So I have 3 equals 9a plus 3b. All right, that's good. Let's take a look at the second one now. The second one, I have 25 equals 4a minus 2b plus 7. I'll subtract the 7 and make that as simply an 18 here, and get rid of the 7 completely. And there's our second equation. Again, notice that this was really negative 2 squared, which is why it's a positive 4, whereas this is a negative 2 times a positive b, which is negative 2b. Now we have a system of linear equations. Let's go ahead and combine them. Either we can solve them with a matrix or combine them using substitution or elimination. A matrix is simply the easiest way to do it here. I mean, you could use substitution or elimination also. I guess we could multiply by 3 and 2 and then add and subtract, but it seems like too much work. So what I'm going to do is this. I'm just going to write 9, 3, 3, 4, negative 2, 18. Okay, that's my matrix. And remember, I write these as if there was an equal sign on this side, right? I always want to write them like this. So when I write my matrix, I see that now it's 9, 3, 3, 4, negative 2, 18. And if you do row-reduced echelon form of this, again, something you haven't learned by hand, but you can do in your calculator for now, you'll get a matrix with the results of 1, 0, 2, 0, 1, negative 5. And what this tells me is that the values of A, or the value of A is 2, and the value of B is negative 5. Again, where does that come from? If you look back at your linear system here, this was A, this was B, right? So this is A really as a column. Well, the 1 is here, so it's 1A plus 0B equals 2, so A is just 2. And then this is really saying 0A plus a b equals negative 5. So b is just negative 5. So what is the overall function? How can I write my final answer? I can write it as f of x equals 2x squared from the a minus 5x from the b, and then remembering that c was 7. So here is our function. So example 5 says to make up your own quadratic function in standard form for the following sketch, and then discuss mathematically why you chose certain values for A, B, and C. Now, the first thing I would think is this. The graph is opening down, so a has got to be less than 0. And that's clear. Okay, so a is going to be something negative. Now, the next thing we have to look at is the axis of symmetry. It's on the left-hand side, right? Here's the axis of symmetry, which tells me that negative b over 2a is a negative number. Right? That's got to be a negative number because that's the axis of symmetry. Well, we started off by saying that a was negative, so that means this is negative also. If this is negative here, then this negative would cancel with this negative, making it positive. So that wouldn't work. So the only thing that has to happen is that b has to also be negative. So we'd have 3 negatives in this problem, or 3 negative signs, continuing or keeping the axis of symmetry to be negative. So as a result, b has to also be negative from the axis of symmetry. And then finally, c we have to look at. Well, c is crossing the axis, right? C is the y-intercept. It crosses down here. Now, how do we know it's the y-intercept? Well, think about it for a second. All of our functions say this, right? That's what our general function says. To find the y-intercept, you set x to 0. So if you set x to 0, these are gone, leaving behind this value. So whatever this value is, and you can try many graphs, try as many graphs as you want on your calculator, whatever you put as that constant at the end, that's what your y-intercept turns out to be. And since the graph opens down and it continues to cross, and it will cross the y-axis below, right, it'll cross the y-axis below the x-axis somewhere here, it means that the y-intercept is negative. So c is also going to be negative. Now the final thing we have to look at, and this is a little bit tricky, is the fact that b squared minus 4ac has to be a certain value also. So far we have 3 constraints right here, right? Constraint number 1, constraint number 2, constraint number 3. The fourth constraint is looking at our roots. Well, we have 2 roots, and they're real roots and they're distinct, which tells us that the discriminant has to be positive. So the fourth condition we have to say is that b squared minus 4ac has got to be positive. So at this point in time, we have 4 different constraints, and if we pick numbers, we can simply come up with an answer. So let's say, for the sake of random numbers, that we choose a to be negative 2. All right, that works. So right away, let's start writing our function. F of x equals negative 2x squared. All right, so that works. Now, b is also going to be a negative number. I'm going to pick a number like b to be very large, because remember, when I subtract these 2 quantities, I want this to be greater than 0. So I want this to be very big, and I want this whole thing to be pretty small, really. So I want this to be large. So let's pick a big value for b. So we'll pick something that's negative, but larger than negative 2, like, I don't know, negative 7 maybe. Okay, so negative 7x. And then for c, remember that we want, since, again, this is going to be a negative number here, it's still going to be a negative number, we want this to be a very small number, or a rather small number. So we could pick something like, I don't know, negative 3 or negative 1 or negative 2. It doesn't matter. Let's try negative 1 here. And then we can see if everything works. Well, clearly the first 3 conditions are met because they're all negative. So let's see if b squared minus 4ac is positive, though. So b squared is really negative 7 squared minus 4 times a times c. Well, when we do this, we're going to end up getting 49 minus, now this is going to be a double negative here, right? Makes this a positive, but another negative keeps it as a negative. So 4 times 2 is just 8, and 49 minus 8 is indeed positive. It's 41, not that it even matters, but the discriminant turns out to be positive. So this would be a good sample function. So the only constraint that was really a concern, once we knew that they were all negative, was the fact that we needed this quantity to be bigger than this quantity, because we were subtracting here, right? We wanted it to be positive. The only way you can end up with a positive when you're subtracting is if you have a big number minus a smaller number. So as long as this was bigger than this, so make b very large so that this is a large value, and pick smaller values for these 2. Example 6 says, determine how many times the parabola y equals negative 3x squared minus 6x plus 4 intersects the following. How many times does it intersect the x-axis, or the line y equals 7, or the line y equals 10? So how do we find out how many times it intersects the x-axis? It's saying how many roots are there. And we know how many roots there are, whether there's 1 repeated root, 2 real roots, or 0 roots at all, based on the discriminant. So let's find out what the discriminant of this is when we set y equal to 0. Okay, so the discriminant would be b squared minus 4 times a, which is negative 3, times c, which is 4. So we take a look at this, and we see that this is going to be 36 minus, now, Minus a negative is a positive, so we're going to get a positive answer here. So no matter what, we're going to get a positive answer. So there must be two intersections. It doesn't really matter what this number turns out to be because it's positive. Okay, if we wanted to know, it comes out to be 48. Positive, positive is still a positive. And when a discriminant is positive, there are two intersections. So that means right away that this graph right here intersects twice with the x-axis. Twice. And already we know it's going to open downward, so it means that the vertex has got to be up here somewhere. Right? It's got to look like this, the graph. The vertex being up here or something, but it's opening downward and it intersects twice with the line or the x-axis, right? Now, what about with the line y equals 7? Remember when you want to find an intersection, that the intersection really means that the two functions you're looking at share a common point. So this parabola and this horizontal line, y equals 7, right? So already I can just dash that line on here, right? Here's the line y equals 7, say. And let's say here's the line y equals 10, right? And the x-axis we already have on the graph. We know that there's going to be two intersections on the x-axis somewhere, and the graph is going to open down, so it could either go like this, right? And maybe it never intersects with the line y equals 7. Or maybe it intersects twice. Or maybe it just touches it once and turns around. We don't know. It could be any of those cases with the line y equals 7. Well, if we want to figure out which case it is, we have to say, well, when two lines intersect, the point that is in common is a solution to both of those lines. So really what you're doing is you're setting them equal to each other. So we need to say, well, since y equals 7 and y equals this whole quantity, let's set those equal to each other and see what we get for an x solution for our discriminant. So let's go ahead and say that. We're setting this y equal to 7 to see when 7 is equal to our parabola. Okay, here's our parabola again right here. And here's the value 7. We want to know when is the parabola intersecting with y equals 7, or when is the parabola's value 7. So let's figure this out. So let's move the 7 over. We're going to get 0 equals negative 3x squared minus 6x. And this is going to be 4 minus 7, or negative 3. Now if I find the discriminant of this, I'm going to see that the discriminant equals, let's see, negative b, or b squared, minus 4 times a times c. Well, negative, negative, negative is now a negative. And this is going to be 36 minus, well, 4 times 3 is 12. 12 times 3 is 36. Well, 36 minus 36 is 0. If the discriminant is 0, it means that there's really only one intersection with the line y equals 7. So in the end, what our graph ends up being, and we can tell already what it's going to look like, is it's going to be this middle option here. That's the actual graph that we're going to have here. Okay, it opens down, it intersects the x-axis twice, and since the discriminant is 0 when we solve this equation, when we set it equal, it must only intersect once, or it must be tangent to the line y equals 7. Now, we can go further and do part C mathematically, but we could see right away that if that is true, then this other line doesn't really exist. It's not possible. So that's our graph right there. So what's the answer for part C? The answer is going to be 0. It's never going to intersect the line y equals 10 because the line y equals 10 is above it. We could prove that mathematically by taking the same equation. Instead of setting equal to 7, set it equal to 10 and see what you get as a discriminant. Let's do that. We get 10 equals, and our equation was negative 3x squared minus 6x plus 4. And if we go ahead and move the 10 over, we get 0 equals negative 3x squared minus 6x, and 4 minus 10 is going to be negative 6. So let's take a look at what our discriminant turns out to be for this. B squared minus 4 times a times c. Well, if we take a look at what we get as a discriminant here, we're going to get 36 minus 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 is still minus. 4 times 3 is 12, and 12 times 6 is 72. So we're clearly going to have a negative answer. This is going to be negative 36. So there are no intersections, right? When the discriminant is 0, there are no intersections, in this case with the line y equals 10 for part C.